We're going to get through 15. 15 is by far one of the more in-depth conceptually chapters. We have to get through the understanding of what is interference, what is divergent, convergent interference. Hopefully those will make sense after a little bit. The other idea is we have to be able to calculate the light and dark circles, and we'll talk about that a little bit more. With a preface, I will tell you your book is actually a very good reference in this. It's got a lot of different pictures and diagrams. I would tell you to look through that if you haven't already. Again, reading through your book is a good resource. Obviously, it's not the best for some because, well, people just don't read the text. Unfortunately, that's the way it is. So let's go get ready to get through some of this. I will tell you here's your objectives as always. Interference, one of the big things we'll have to do, I would like to show this in the classroom. I'm still working through different ways to do this. The problem is it's a monochromatic light source, meaning in the classroom we've got 10 to 12 lights. The problem is that's all giving light in different wavelengths, in different light, in different areas, and it's also kind of spread out. The problem becomes you have to be able to distinguish and decipher one single light bulb. You'll see some of the diagrams later on. It's a single light source giving off a single wavelength of light. I'll probably try and use some of the neon light lasers that we've got, or neon light sources. Short version, that first one's very important. Interference only when wavelengths of the same have to be of the same wavelength, i.e. they're giving off one wavelength of light. You can use others. I've done it in the past. The problem becomes wavelengths of many different lights, or excuse me, lights with many different wavelengths. You have compounding problems. It's kind of like finding where a single student is going. That's kind of easy. Finding out where 12 different students are going, okay, you might be able to do it. 50 different students, you don't know where they're all at. So it's kind of one of the problems I'm working through for the monochromatic light waves in class. I will tell you the constructive interference portion. You guys understand this. Constructive interference, constructive sounds. Basically, same reason why Arrowhead Stadium is incredibly loud. If you can get everyone on the same beat, the same wavelength, you can get everyone with a constructive interference. The destructive interference, you guys have seen this too, our student body. When they start going and you have the 2 or 3 students that are just kind of off beat, that's kind of where I'm at. It destroys kind of the whole total amplitude of a wave, and we'll talk about that going forward. So let's get right into it. Interference. You want to look at the 2 red as being your first 2, your purple being your actual end resultant. So in this case, if you notice the wavelength from start to finish, from in this case medium to medium, is actually the same wavelength. So those 2 are going to be on the same side. They're going to add together to make a resultant wave that is bigger. Obviously the same happens on the trough, crest, trough. Since they're at this same wavelength, they can actually make constructive interference. Now, notice the second diagram. Again, you want to look at the first 2 red lines first. Still the same wavelength, but in this case, they're actually transposed. So you notice they're on the opposite sides. One's a positive, one's a negative. That resultant purple wave is not as tall as either destructive interference. Again, it only works when they're on the same wavelength. So notice, make certain you understand that and can be able to explain the difference between constructive and destructive happening within the same wavelength. Again, short version, coherent, incoherent light, sources for light, non-consistent, incoherent light. Basically, several different light sources, not on the same wavelength, all the things that you talk about having a bad day. This is, for a light source, everything's inconsistent. Incoherent, hopefully makes sense. Coherent, phase difference is constant. So there you have. So one of the big things, coherent light. Light from a single source. Incoherent light, they've got it kind of drawn out as, hey, look at all the different waves, blah, blah, blah. Coherent light, light is coming off in consistent patterns, same wavelength, one single source. Again, this is kind of hard to picture because most of the light we have in use for everything is incoherent. It's got the red, the blue, the green. It's got all your colors of your spectrum. Well, that's all different wavelengths. So unfortunately, it's incoherent light. Coherent light would be a single wavelength of light. How often does this happen? Honestly, you very rarely will ever see it. It's a reflection. Hey, you see it all the time. Coherent light coming off a plant, green, typically in the same wavelength. Most of the time, the coherent light coming off a plant is one color of light, typically. Everyone can sit there and go, well, I've seen a plant that's got, yeah, I got it. But example, one single blade of grass should have the same green spectrum through it. It might have a little variation, but that would be a kind of a way to get coherent light. Most of the time it's actually through a laser or a projection or actually a filter being applied, whether it's a green, any color filter really works, or actually a prism that breaks apart the light and blocks out certain light. So incoherent light, everything we do, kind of the amusing joke everyone likes to say, well, it's incoherent light. Yeah, that's why we have problems in schools. Anyway, again, interference. Now, here's where we get to the hard part. Interference in your book is actually very, very well defined. There's a couple page, like 533, I think it's 540. I want to say 542 or 547. It'll actually show you a very good picture of this. I probably should add it to the slideshow when I get a time. So, interference, basically, when light travels through two very, very narrow slits. Example, I mean, honestly, think of a single slit in a visor. Now put a second one. You can actually see this. We'll show you one way to calculate it here. So, good news is it actually creates light and dark. Bad news is we're going to have to calculate how we do it. This should make sense when we sit there and look at that first diagram up in the upper left-hand corner. You have two slits, wavelengths of light coming together and hitting in the center or right across the normal in the very center. Okay, look at that. Constructive interference, two waves coming together, same wavelength, should be a very tall wave, constructive interference. Now, if we move that down below, we're going to go down the diagram, the length plus one of the wavelengths. So we have to sit there and calculate down how much a wavelength is. That should be another constructive interference. We'd see another band of light. So the first two on the left, band of light, band of light. Now, if you're still thinking waves, if you sit there and say the wavelength plus 1/2 of a wavelength, well, that should put one wave going up, one wave going down. It's exactly right. That's what this picture is. And the resultant of one wave going up, one wave going down would be destructive interference. Well, if one wave's going up, one wave's going down exactly in the same wavelength, they cancel each other out. There would be no light shown. Good example is this, page 533 has a very good picture along with 534. Two good pictures, one's in green, one's in blue, or excuse me, one's in green, one's in red. Two different wavelengths of light showing the exact same property. Basically, you'll understand even on the slit width on page 533 has the diagram shown out as well. So the idea, if we add a distance, the bottom diagram in the lower left, the distance is a wavelength. So we start in the center, that's a bright circle. We go down a wavelength, however much a wavelength is, depending on the color of light, depending on the frequency of light, the wavelength will give us how far down we should have another band of light. Half the way in between will be destructive interference. There's not going to be any light there. Constructive, light in the center. First band, the black, is going to be destructive. It's half the wavelength. Full wavelength down, that'll be another band of light, and so on. So until it fades away. So here's the math, unfortunately. You can sit there and say, okay, there's our distance, d sine of theta. This is actually what's going to give us our angle for L1, L2. We'll use those a little bit more in class. Here's where you have to start going, okay, we got to put some terminology to this. Central bright fringe is the order number. Basically, symbol is M. So in this case, the central bright fringe at Q equals 0. M equals 0, 0 order. 0 order, and again, if you look at your book, page 536, this is actually kind of shown with an example for, I think it's yellow light, and they didn't tell me what color. Okay, so anyway, depending on the light. They're actually using yellow light, which contains 3 or 4 different colors. So you have 0 or m equals 0, 0th order, 0th, or central maximum. You'll hear me use central maximum the most. Why? Because it's what I was taught. Then you have first order maximum. So you have central maximum, then you have your first order maximum. Again, if you look at page 536, it's right there for you. So equation, we're going to get through these. We'll actually do the math in class. Here's your example problem. If you want to go ahead and write it down now, we're not going to actually calculate it in this video. And there's the answer. Cool. When we talk about diffraction, this is the hardest second part of this. Diffraction, change the wave. We've already talked about this a little bit when we talked about light in lenses and mirrors, so it shouldn't be anything different. This is where we sit there and go, okay, destructive interference. This is actually calculating it. Central bright fringe, imagine that. This is actually for diffraction, it's going to be a single slit through a single slit. Now here's the hard part, is everyone sit there and has seen their shadow. This is what it's really trying to calculate. How big is your shadow? How little is your shadow? And then how is that fringe around your shadow? Can we actually calculate that? Yes, the answer is, but the problem becomes there's a lot of math to it. So we'll probably calculate the first or second order fringe and leave all the rest of them alone. Because, well, frankly, it takes a long time. Again, here's your example. Here's your diagram. Again, A, B, as the fringe goes through, it's going to start to bend. We want to know what that wavelength is. And then there's all your diffraction pattern. Again, your central maxima, secondary maximas. So, and I think we have diffraction grading. We are going to talk about specifically in class. It's a way to bend light. And we'll do the calculations in class. Why? Because I don't want to take your time now. Resolution 2 light sources, we will have to do, and we'll discuss. We're not doing the calculations on those because that leads you down a path to lasers, which we are not built to handle, and frankly, we don't have the time. So that ends this chapter 15, so you should be good with chapter 15. Again, you might want to watch this. I would always recommend you going back and reading the notes, reading them through the book, if nothing else, to give you more examples of the exact same thing I went through here in the video.